Hi guys, I want to go through the multiple choice questions on this molecular geometry. So in OneNote, this is, I'm putting this in my content library, but this has been distributed to you, this MCQ Vsepr. Let me get rid of that. I'm going to walk you through these multiple choice questions to show you, how to put these molecules together and get their geometries using that, I think that helpful chart with the summary of the shapes based on the electron domains. So number one here, which molecules correctly match with its shape as predicted by the theory? Okay, so we want to go through and draw these structures out. And remember, I mean, who knows what this test is going to look like? You'll have like one question probably on molecular geometry and talking about intermolecular forces and things. So this is just really a practice in Lewis structures and just so you get the repetitiveness of it. So this PCl3, phosphorus has 5 valence electrons. Each chlorine has 7 times 3 is 21. So our picture is going to have 26 electrons in it. So we start by putting the phosphorus in the center. We put the chlorines around it. We start by connecting everybody with single bonds. So that's 6 electrons. I put 18 more electrons in. So 6 plus 18 is 24. I have 2 more electrons, and they're going to go on the phosphorus. So when you have so look at your domains. We have 1, 2, 3, 4 domains. 3 of them are bonds, and there's 1 lone pair. When you have 3 bonds and 1 lone pair, that would be trigonal pyramid. So that's actually the correct answer. And again, you can refer back to this chart. 3 bonds, 1 lone pair gives you a trigonal pyramid geometry. Now let's look at the other ones just so you have an idea of what's going on here. OF2, oxygen has 6 valence electrons. Fluorine has 7 times 2 is 14. 14 plus 6 is 20 total. I'll put the oxygen in the center. I'll put the fluorines on each side because I don't know what shape it is yet, so I'll just start by distributing them. Electrons, electrons. So that's 4 electrons gone. I have 16 left. So I just put in 12. So I have 4 more electrons. Those 4 electrons can go on the center atom of oxygen. Now, when you do this, if you had to draw this molecule and you left it like this and it was like, hey, what shape is it? You're like, oh, it's a straight line. It's not a linear molecule. Look at your domains. You have 4 electron domains in total. You have 2 bonds, 2 bonding domains, and 2 lone pair domains. According to this chart, when I have 2 bonds and 2 lone pairs, it's a bent molecule. And a bent molecule that has a total of 4 domains around it, we start out with that tetrahedron electron geometry, which tetrahedrons have a 109.5 degree bond angle, but lone pairs will actually squish the atoms together closer, decreasing their bond angle. So that's a bent molecule with a less than 109.5. So looking at this answer choice, this would be wrong, right? It looks linear, like, oh, I drew it in a straight line. It looks pretty like that, but that's not what it really looks like. ClF3, chlorine has 7 valence electrons. Each fluorine has 7 times 3 is 21. 21 plus 7 is 28. So I'll start with that chlorine and I'll put the fluorines around it. I've just put in 6 electrons, so I have 22 left. So I'll put in the 18 that will fulfill the octets for my 3 fluorines. That gives me 4 left. When I have extra electrons left, they go on the center atom. Chlorine can exceed the octet because it has, it's a third row element. It has the ability to expand it. So looking at my electron domains around my center atom, I have 5 total domains. I have 3 bonds, and I have 2 lone pairs. Now, anytime you have 5 electron domains in total, the electron geometry, that would be trigonal, bipyramidal. And that was covered in the last video. Now, when I start to substitute in the lone pairs, I put 2 lone pairs in there. So 3 bonds and 2 lone pairs. 3 bonds and 2 lone pairs. Here's a lone pair, because those start to go around the perimeter atoms. Okay, we start to, when we do start to put in lone pairs, we do that around the perimeter first, those three that are kind of branching off of that main axis. That gives us a T-shaped molecule overall. So this says trigonal planar, because you're like, oh, I have three things. Look, it looks like a triangle. No, it's actually going to be a T-shaped molecule. Because what we did here, here's our starting point, right? So these, let me change the color. These three are kind of arranged in a trigonal plane. And the two ones that I left blue are arranged in a straight axis. When I start to put in lone pairs, I will take out these first. So here's a lone pair replaced. Here's a lone pair replaced. So what do I have when I flip this onto its side? I have a T. Okay, because this one's actually coming out like towards me a little bit. So I flip it on its side, I have a T. SF6, hexagonal is not even an option. Okay, it's not a thing. So let's look at, let me erase some of this stuff. So SF6, sulfur has 6 valence electrons. Each fluorine has 7 times 6 is 42. 42 plus 6 is 48. So I have this sulfur, and I'm just going to start throwing the fluorines around here. 4, 5, 6. Okay, so if I have 6 domains, the electron geometry would be octahedral. Okay, so I'd have these, let me straighten this out a little bit. I would have, whoops, these fluorines would be arranged on like a vertical axis, and then these other 4 fluorines would be arranged in a cross pattern around like the equator here. Okay, now since all 6 of these domains, oh, I have to fill in my electrons, but so I did 12, and here's 6 times 6 is 36, so 36 plus 12 is 48. So if you had to draw a Lewis structure and you left off these dots, you would not get the point. So there's my molecule. I don't have any lone pairs left over. So I have 6 domains. All 6 of them are bonding domains. So this would be an octahedral shape. 6 domains in total, all of them bonds, octahedral in shape, and all of the bond angles would be 90 degrees. Okay? For number 2, on the base, this one's tedious, of course, because you have to, well, the first answer was the right one, so yay, but you kind of have to go through all of them. For number 2, they're giving you a molecule and they're giving you these options, which is nice. So based on this Vsepr theory, what geometry is predicted for the central sulfur atom in SOCl2? So they're telling you the sulfur goes in the center. So let's count. 6 valence electrons for sulfur, 6 valence electrons for oxygen, a total of 14 valence electrons for chlorine. So 14 plus 12 is 26 electrons are needed. So we'll leave the sulfur in the center because it's telling us that. Let's just throw the other ones around here. Bond them into the center. So that's 6 electrons. I have 20 left. Let's complete the octets for our perimeters. 2, 4, 6, 2, 4, 6, 2, 4, 6. I just put 18 electrons in. I have 2 left. The leftover electrons will go on the center atom. So here I have 4 electron domains. 3 of them are bonding domains. So the four domains in total means the electron geometry is tetrahedral. 3 bonding domains, 1 lone pair, tells me that it's a trigonal pyramid. So this would basically, be the same type of structure as like a ammonia molecule. This would be polar, right? It's an asymmetrical molecule. Especially if you see, because you have the oxygen and then you have 2 chlorines, but anytime you have a trigonal pyramid, it's going to be an asymmetrical molecule. Number 3, this is a good question. For which species is the electron geometry around the center atom of the Lewis dot structure the same as the geometry of the atoms? So I want the electron geometry to be the same as the molecule geometry. So what does that mean? I don't want to have any lone pairs, because lone pairs start to throw off that geometry. So I want all of my electron domains to be an atom attached to that center. So carbon dioxide looks like this. So around the center atom, I have 2 domains, no lone pairs. Well, there's my, it's a linear electron geometry and it's a linear molecule. So there's my answer. So I don't have to go through the others. Remember, if you are drawing the Lewis structures for these ions, when you're counting your electrons, you got to add in an extra electron because it is negatively charged. 4 is good. Bond angle questions come up. In which choice are the molecules listed in order of increasing bond angles? So we want low bond angle to a high bond angle. Okay, so this is good practice because these are, it's the same 3 molecules, just in different orders, so that's good. Okay, so we have a water molecule. So water molecule is something you would be drawing in your sleep, bent. Okay, methane. So these 3, these were like Regents ones that were drilled into your head too. And methane. Okay, so for all of these molecules, all 4 of them have 4 electron domains. So the electron geometry for all of these molecules is tetrahedral because all 4 of them have tetrahedron because they all have 4 domains. But the only molecule that is a tetrahedron in actual molecular shape is going to be the methane because all 4 of those domains are bonding domains. So for a true tetrahedral molecular shape, the bond angle is 109.5 degrees. Now, starting to replace a bond atom with a lone pair, that takes us next to ammonia. Ammonia has 3 bonding domains and 1 lone pair domain. So the shape of this, electron geometry-wise, it's still a tetrahedron, but molecular geometry, it's a trigonal pyramid. That's what you get when you have 3 bonding regions and 1 lone pair. Now, we start out with that 109.5 degree bond angle because the electron geometry is a tetrahedron, but when you have a lone pair, when you start to substitute in lone pairs, the lone pairs of electrons, those 2 electrons are Are you freaking kidding me? Please tell me we're still rolling here. These electrons will repel one another and push against those atoms, which will push the atoms closer to one another. So this bond angle would be slightly less than 109.5 degrees. Now, if I take another atom and replace it with another lone pair, so here I have 2 bonds, 2 lone pairs, the molecular shape would be bent or angular, okay? And now, in terms of bond angles, these are pushing even more so, which will decrease this bond angle even less than 109.5 degrees. So looking at these answer choices, if I'm putting this in order of the smaller bond angle to the larger bond angle, water would have the smallest bond angle because it has the 2 lone pairs and 2 bonds. Ammonia would have the next highest bond angle because it only has the 1 lone pair with the 3 bonds, and then methane would have the highest bond angle at the standard 109.5. Number 5, what's the shape of the ClF3 molecule? This will be the last one that I go over because I think the others, you gotta get the idea. So ClF3, chlorine has 7, each fluorine has 7, so we have a total of 28 electrons. Chlorine will go in our center. Let's throw the fluorines around it, so that's 6, we have 22 left. There's 18 here. So there's 4 left. They can both go on that chlorine center. because the chlorine can expand its octet. Now, looking at our electron domains, we have a total of 5. See how methodical this is? It's actually pretty beautiful. So we have 5 electron domains. So the electron geometry, when you have 5, is trigonal bipyramidal. Okay, so we have this sort of scenario happening. We have, in terms of regions, these 3 would be oriented along a flat plane, like around the center here, right? So now we don't have 5 atoms bonded though, like I made in this picture. We have 3 atoms bonded and 2 lone pairs. When you start to substitute in lone pairs, you substitute them in along this plane area. So we'll take out 1 atom, we take out another atom. Now what are we left with? We're left with this vertical axis, and we have 1 sticking off of it at a 90-degree angle. So what does that give me? If I flip this on its side, it gives me a T-shaped molecule. Okay? So I hope that gives you a nice practice with it. I want you to try these other 5 now that you kind of see the thought process involved. So this takes Lewis structures and just adds on and looks at the actual molecular geometries.